Welcome again, betas, to a new lesson. So this is going to be the final lesson of proving vector identities from the Griffiths textbook. And we are left these three, 9, 10, and 11 from the second derivatives. So let's start with the number 9, and we are told that the divergence of the curl of any vector is 0. So we are going to prove that this is true. We start by translating into index notation, which is simply the contraction of the del operator with the vector curl of A. And we can pull out the Levi-Civita symbol out of the derivative because it's always constant. So we are going to assume now that we can do a thing which is swapping like the partial derivatives. Okay, we are going to suppose that it stays the same thing, like it's the same thing. Doing first one partial derivative and then another, than doing first the other one and ending with the first one. Okay, so we can swap partial derivatives. Not every function behaves this well, but we are going to assume that we are working with a vector whose components have functions that they behave well. Okay. So strictly speaking, this is not a proof for any vector. Okay, this is a proof for a vector that behaves like well enough. So we are going to do a little trick here, which is that we are going to demonstrate that this is 0. Okay. So I'm going to bring this down here. We know we can swap partial derivatives, so we are going to swap them. Okay. ijk del j del I ak. Okay, so far so good. Now we are going to interchange the indices of the epsilon. So we have minus epsilon j epsilon I k del j del I ak. So now we are going to note something. Okay. So watch this. It's the same. Imagine that we contract any vector with other vector like a and b. It's the same rating ai bi than aj bj, or ak bk, or an bn, and you get the idea. So dummy indices, they are just labels. Okay, we can change the letter by anything. So here we can change the labels. Okay, so be careful, we are not changing indices or swapping indices. We are not swapping indices. We are changing the labels. So we can change the label j for I and the label of I for j. Okay, so we have ijk del I del j ak. Okay, the sum is not going to change. Okay, this is just the sum of the components ai bi, the sum of aj bj. So changing the label is not going to change the sum. So this is the exact same thing. We have only changed labels. We haven't swapped any indices. We have swapped indices here and here. Okay, in the first two steps we have swapped indices, but here in the last one we have only swapped labels. Okay, now because this is equal to this thing, we can pass this on the other side. Okay, I'm going to copy this. Well, this is like the same thing for every step. We're going to change this to the other side, and we are going to have 2 times epsilon ijk del I del j ak equals 0. The 2, it can go out, and we have demonstrated that this is 0, thus this is equal to 0. So we have assumed that the vector A behaves well enough so that we can interchange partial derivatives, and we have done this little trick of changing labels and swapping indices. More formally, we'll see that if we have an antisymmetric tensor, for example ij, let's say that this tensor is antisymmetric, and we contract it with a symmetric tensor, this is 0. Okay, so we just really contracted like these two indices, which I mean the Levi-Civita symbol is completely antisymmetric, so it's like an antisymmetric tensor with del I, del j, and you can swap them, so this is like a symmetric tensor, so like this property holds, and you prove this property with the steps that we have done. Okay, but we'll see this later. You just have to say what I said before. So we have proof number 9, and now we are going to do number 10, which is basically the same thing. Okay, so in number 10 we have that the curl of any gradient is 0. So in index notation, this means that epsilon ijk del j del kf, this is exactly the same thing as before, but instead of having a vector a, we have a scalar function f. So we are going to do the same thing. Okay, so we are going to swap the partial derivatives. Again, we suppose that f is a well-behaved function such that we can interchange partial derivatives. In physics, almost every function we can do this. Okay, it's only like weird functions and exceptions, but almost any function we are going to work in physics, we can do this thing. Now we are going to interchange this time the j and k indices. And now we are going to relabel, well, we are going to label again this second and third slot of the Levi-Civita symbol with the partial derivatives. So now we have that 2 times epsilon ijk del j del kf is 0. So it's basically the same as before. Now we can kill the 2 by putting it in the other side, and this is 0, which is basically the curl of the gradient of a function. So the only thing that is tricky in these two demonstrations is like these steps of interchanging well, you have to suppose that you can interchange partial derivatives, and now you swap indices, then you have to relabel the indices, and it's done. So it's easy, but you have like to think what it means, what's the meaning of the labels and its names that you can interchange them. Okay, so let's finish with number 11, and we are given that the curl of a vector is the gradient of the divergence of the vector minus the Laplacian of that very same vector. So we may translate this into index notation, and we have epsilon ijk. In the second slot we have the del with a j, and in the third slot we have this vector, which is the curl of a. So its free index, which is contracted with the third slot, is going to be k. And now we have two dummy indices, m and n, del m and an. So as in the previous one, we can pull out the epsilon because it's constant. So we're going to have epsilon ijk, epsilon kmn, and now we have del j, del n, and an. So we are going to use again this property of the product of two Levi-Civita symbols, and we are going to have that del mi del nj minus del mj del ni. And now we have here the same thing. So we are going to distribute this, and then we are going to collapse all the Kronecker deltas. and let's see what we have. So now we are going to collapse the M with the I. So we have del I, and now we are going to collapse the N with the J. So we have AJ. And now we are going to collapse the N with the J and the N with the I. And this, in vector notation, well, first of all, remember that we can interchange partial derivatives, okay, because we suppose that we are working with vectors and functions that behave well enough. And now this, into vector notation, is just, the free index is I, so these two are contracted, and this is just the divergence of A. We see that the free index I is indeed like the free components of the nabla vector, and now we have minus. Now here both dels are contracted, so we have the Laplacian, and the free index, which goes with the vector I, is indeed this vector which determines the components. And it's the same thing, we have a gradient of divergence of A, gradient of divergence of A, minus Laplacian of A. So we have finished lesson 1.1.3, and we have demonstrated all these formulas from the Griffiths textbook. And then we'll go to lesson 1.1.4, and we'll actually learn the difference between up indices and lower indices. So stay tuned for the next lesson, and see you later.